for the first question and the practice exam.
Yeah, go ahead, please.
He said key that U2 is greater than U1 and F external is greater than 0. Can you like go briefly how did you determine that things like?
Also, the first question in the practice
Yeah.
exam, the full question. Okay, so just give me 1 second. I will share my screen and then we can go with that. Okay. So, problem 1, practice exam. All right. And then O1 and then Sophia. So Talal, you can if you we can then go to next questions if you have more, but and then we'll go to Sophia. So okay, just can you all see my screen?
Yes.
Okay, so I'll do practice exam. Practice exam. This is problem 1, and so we have been given U1 A1 and then U2 A2, and so the question is, how did we do this? So we know from continuity equation that V dot N dA over control surfaces is equal to 0. So this simply gives out A1 U1 is equal to A2 U2. So hopefully this is clear, Talal. And then from the momentum balance, that's where the question really comes in. We should remember that F external is equal to rho V vector V dot N dA. And so the first case, the V dot N is negative because normal vector points outwards always, but the velocity is positive. So I'll get a rho U1 square A1 and then I'll get a rho U2 square A2. And so from here I get rho U1 and I can substitute U1 A1 is equal to U2 A2 from here. So I will get F external and U2 is greater than U1 because A2 is smaller. So I get a positive number out. Make sense, Talal?
Yeah. Thank you. And what if the question was asking about like a diverging tube, not a converging?
Yeah, in that case, it will be negative. So then
Everything
basically,
would be switched, right?
correct. Yeah, exactly. So if it's a diverging tube, so if you have a tube like this, if this was A1, U1, A2, U2, everything will remain the same, but now U2 is less than U1, so F external would be negative.
Okay.
Yeah.
Thank you.
All right. So I think it was O1 next, and then Sophie, and then we go to Ari. Yeah. Go ahead, O1.
So I have a question about 4B. In that question, we are looking to solve for like U2 and U3. And in your solution and on the video on YouTube, you solve for U3 and you get that U squared equals, or you get that U3 equals U2 times the square root of A2 sine of theta 1 over A3 sine of theta 2. And then you solved for U2, but I was just confused on where the original U2 went because I don't know. Yeah, I'm just confused on where it went. That's all.
Okay, sure. Now I can answer a question. Let me just make sure because I have to look at the exact step that you're talking about. So yeah, let me take a look and then I will answer your question. So this is for problem 4B. So you're asking where U2 went, right? That was the question.
Yeah, we solved for U3, and then when we went and plugged U3 back into the equation to solve for U2,
Mm-hmm.
the U2 just like went away, and I'm confused why.
So I think maybe I'm missing the point. So I hope it is clear. So for from the y direction velocity, right? From the from the y direction momentum balance. So look at the f of y, right? So if from the y direction momentum balance, it's if f is only in the z x direction. So from the from the y direction momentum balance, I get a relationship between u2 and u3. That's the top equation written just below the 4b, right?
Yes.
And so that's essentially where I have now substituted so I got a relationship between u3 and u2, and then I'm saying that I substituted for u3 as a function of u2 there. And then you're asking me, yeah, so I guess, does that make sense? So that's all, it's just substituting u3 as a function of u2 in back to this equation between the two equations.
Yeah, so
So
we got U2 equaled A1 V1 over A2 plus A3 times the square root of A2
correct,
sine theta over A3
correct,
sine theta.
correct,
But right above that, we got that U3 equaled U2 times the square root of A2 sine of theta over A3 sine of theta. So I'm just
correct.
wondering where that U2 went.
Yeah, because I've substituted that u2 and then the u2 has been factored out, right? So if you substitute u3 as u2 times a factor, then I can factor out the u2.
Okay. Okay.
Make sense? So if just substitute this back, so the blue arrow, just substitute this back to u3, and then as you can see on the right hand side, both the terms have u2,
Okay.
and so that has been factored out.
Okay. Thank you.
Yeah, sure. Yeah. Yes, Sophia, go ahead, please. Yeah.
Okay, I just have like more of a general question that's like appeared on the homeworks and it was on the practice exam.
Mm-hmm.
But whenever we're doing the F external balance,
Mm-hmm.
and whenever they like tell you that they have a pressure, I
Mm-hmm.
get confused like when to subtract the pressure, when to add the pressure from
Okay.
like,
From the
and like
mm-hmm.
yeah, and specifically on homework 5 with question 1 and 2.
Mm-hmm.
For question 1, it was added, and then for question 2, it was subtracted. And I
Yeah.
just don't get like how to know which one is which.
Okay, sure, sure. Yeah. So how to deal with pressure, deal with P in momentum balance, right? So that's mainly that's the question. Basically, what's the process? Okay.
Yes.
So first thing to note always is pressure force is normal to the surface. Okay. So if we give you, and I can discuss some cases which will make it hopefully clear, normal to the surface. Okay. So let's imagine if I have a pipe like this. Okay. And I have some pressure P here. So the pressure force will always be normal to the surface. So that's the first thing. So a pressure force is a like pressure force is a part of P external. So pressure force is added to P external. Oh, sorry, added to F external. So it is always going to be added to the F external side. That's second part. It is always going to be normal to the surface, and it is going to be direction of push direction. So I'll explain what I mean. Direction is push. And we'll discuss what that means, and that's probably will clarify the positive and negative. So if my pressure is P1 here, and this is theta, let's say this is an angle theta with the horizontal, and this is A1, then in the F external part, F external, and I have rho V vector of V dot NdA. In this part, I will add, as you can imagine, P1 A1 cos theta in the I hat and P1 A1 sine theta in the j hat. Okay, that does it make sense first?
Yes.
Okay, now if I had P2 on the other side, P2, now this will push in this direction, in the opposite direction, right? It's not going to push in it's basically going to push. It's again normal. It's normal to this side, but it will push in the opposite direction here. So if this is theta, then this is theta. So then this would become minus P2 A2 cos theta I hat and minus P2 A2 sine theta J hat. So pressure will always push, it will always be normal and has to be a part of F external. Now I can add an anchoring force on the other side, like Fx, Fy, like the problems add, but pressure will always go on this left hand side with this sign. So let's do one more example of this, which will hopefully make it clearer. So this is one example, but now let's say if I had something like this, right? P1 and P2 here. Again, pressure will always push here. So F external again, rho V vector V dot and dA. And I'm kind of right now doing it in the vector form, but you in your exam and your homeworks you have done in X and Y separately. This is just to show you to like that both it can impact both directions. And so in this case, P2 will again push. It's always pushing. Okay, so it always pushes. So this will be P1 A1 I hat plus P2 A2 J hat. Makes sense? So this will enter the positive, it will enter the X direction balance. This will enter the Y direction balance, and this is the sign.
Okay, that makes sense.
Okay, and if I had that in this way, P1, P2, then I'll have P1 A1 I hat minus P2 A2 J hat. Okay.
Okay, and this is always on the left side first.
Correct. It's always on the left side, and then rest of it is just manipulating the equation to find a value or find an expression. But you always add it only on the left hand side, and then you can manipulate later down. That's different, but it is a part of a F external.
Okay, and then one last thing, because in some cases it's just P1 A1 minus f of x. Is that just because they're flipping the sign so that the pressure isn't negative?
No, it should be because of the fact that Fx is pointing like this arrow of the anchoring force is this way, or that will give you minus Fx.
Okay.
So
Okay.
the arrow of the anchoring force will determine that sign.
Okay. All right. Thank you.
Sure, yeah. I know we have several students right now, so I'll go to Ari next, who has raised their hands, and then we can go through the rest of the students as well. Yeah, Ari, go ahead, please.
I have a question on problem 3 on the practice exam.
Mm-hmm. Yes,
And
please.
it's a quick question. I just wanted to ask if that formula, it's something that was like given in class and we can use on like every like cylindrical pipes.
Yeah,
It is?
absolutely.
All
Correct.
right,
Yeah, any
great,
physical pipe is that formula. Yeah, absolutely.
great, thank you.
Sure. Other questions, anyone? So I've gone to Owen and Ari and Talal also. So any other first, I'll just make sure any other student has a question, and then we can come back to you, Talal and Owen. Okay. Any other questions, anyone? Feel free to unmute and ask ask. Okay, nobody is asking, so please feel free to unmute. So now we are repeating students, but you are welcome to unmute and ask. Okay, so I'll go to Talal and then Owen. Okay, Talal, go ahead, please.
Yeah, I just have one question about the anchoring force. Where do you put it in is it on the side with the F external or the other side, like usually?
Can you repeat the question again? Sorry.
For the anchoring force that you just
Anchoring force? Yeah, anchoring force is always on the left-hand side as well.
with the F external, right?
Correct, absolutely, yes.
Okay, and can you go over the integration for 4A in the like go over because you did not like write the steps for integration and getting the U of Y and then
You mean 6 of A or
I think it's 4A.
4A in the practice exam, or sorry, can you just maybe clarify which problem you're taking?
Yeah, it's on the practice exam, but I think it's let me check which question it was. Oh, 6A, I think, yeah.
Okay, yeah, 6A. So 6A, so
That's
the
right,
last question is about 6A practice. Yeah, for sure, yeah. So let me do it now. So practice exam. Exam-6 of A. So the question is, let me just write it down. So it says, I just write down the Navier-Stokes equation, rho del U by del T, U del U by del X, U del, V del U by del Y is equal to minus del P by del X plus mu del square Vx, sorry, mu del square U by del X square, del square U by,
Professor Gupta,
yeah.
my question was gonna be about your thought process about how to cancel all these things out.
Mhm.
So just to save time, is there any way that you could do that while
Sure.
you're answering this question?
Yeah, absolutely, for sure, yeah. So I can also give you all, like, as I had mentioned in the class as well, in all of these problems, and whenever you will do this in this course, and only in the advanced courses does it start to change, you will find that we will always cancel the left-hand side, okay? It's good to kind of make sure you understand why, so that in case there is a question where we don't do that, but in any long problem, you will always see we can cancel everything. So this is steady. So we'll cancel because of steady. And remember that U is equal to 0. Sorry, V is equal to 0. And we also have the continuity equation. And this goes away. So this means del U by del X is equal to 0. So this implies U is a function of Y only because del U by del X is 0. So I believe the problem should have explicitly stated, if not, I believe it should have, it's a steady problem, like it's clearly states, and unidirectional. So V is 0. So this is unidirectional. It is only inflowing in one direction. So this is why we can say V is 0. And from continuity, we can say U is a function of Y. This will always be true in your problems. So you can very quickly just, we say continuity, it's U of is a function of Y. Then this is steady. So steady means time derivative is 0. So that's hopefully clear. Then this is 0 because of continuity equation. Del U by del X is 0 from this point. So this is continuity equation. And then V is 0. So this term is also 0. So as you can see, the left hand side goes to 0. This is all 0 because simply V is equal to 0. So V is equal to 0, V is equal to 0, V is equal to 0. Then this is 0 because del U by del X is equal to 0. And then V is 0 and V is 0. So this will be identical. Any problem you will get in unidirectional flows, this is identical. So just kind of to save yourself time, make sure you know that you can save time by just focusing directly on this part, that minus del P by I'll just switch over to the other side. Del P by del X is equal to mu del square U by del Y square, or rather d square U by dy square, because it's not a function of X anyways. D square U by dy square, and del P by del Y is equal to 0, which implies P is only a function of X. It's because P is a function of X, this will become dP by dx. So tomorrow also, or any problem we do in this class really, this equation is what you will get always. Okay, so you can save time. I wouldn't say just skip the steps completely, but you can be fast. It will just take you a couple of minutes to just cancel out time. We are not looking for you to give us any detailed explanations or anything like that. So you can save time. This is what you will get out. And now, as we had discussed in the class, because this is only a function of X, this is only a function of Y, a sine X can never be equal to a sine Y, or an X square can never be equal to a Y square always. For them to be always equal, a function of X to be always equal to a function of Y, both of them are constants. Okay, and both of them are constants. You can essentially say this becomes dP by dx is a constant. So I'll replace this as delta P by L. And again, this is something you can expect. So first, let me stop here because this was, I think, a question. Does this make sense? Like, does this, do these steps make sense first? Any questions at this point? Yeah, I have something on the chat. Okay, all good. Okay, sounds good. So this is good. And now let's go to the next step. And so the next step is where all the magic will happen, basically, which is the boundary condition. So make sure that you are at this step, because this step is always going to happen in these problems. If pressure drop is 0, like the case is in the shear flow, the left-hand side simply goes to 0. If it's a pressure driven flow, then you have a delta P by L. If it's a pressure driven plus shear driven flow, then also you have a delta P by L. So this step is going to be the same, identical. Okay. Now this is where the magic will change, where you basically can expect differences is the boundary conditions. So the boundary conditions is the boundary condition at the lower plate, which is y equal to 0 in the practice exam. This is equal to 0, and at y equal to capital U, at y is equal to h, it's u naught. So this is the step that's sort of important. And these boundary conditions will depend on the exact system you have. If the bottom plate was moving, then u of at y equal to 0 will be u naught, and u of capital H will be 0. So if it was reversed, that's what will change. So now we will do integration. So we will integrate. It's just easier to take the mu on the other side. So I will integrate it like this. Delta P by L, d square u by dy square. Okay, so this is the equation. Let's integrate once now. Integrate once with y. And you'll get 1 by mu delta P by L dy is equal to d square u by dy square dy. Okay. Sometimes my u's and y's are confusing, so let me try to clarify. It's d square u by dy square dy. So in the right hand side it becomes delta P by mu L times y plus c1 is equal to du by dy. This is the integration constant. Then we will integrate again. Integrate again. You get du by dy delta P by mu L y plus c1 dy. And right now you basically will get this is equal to u delta P by mu L y square by 2 plus c1y plus c2. Okay, so this is what you get out. Any questions until this point? All good? Okay, so I'm assuming everything is being followed now.
Yeah.
Yeah, any questions, Talal?
No, I meant everything is good.
Oh, okay, sounds good. So now we have u of 0. I believe u of 0 was 0. Yeah, so u of 0 is equal to 0. So this implies that I'll substitute y is equal to 0. So this is 0 plus c1 times 0 plus c2 is equal to 0. So this goes away, this goes away. So this means c2 is equal to 0. So that's the first thing. So C2 is basically 0. It doesn't enter my equations. Then I have u of h is equal to u naught. So this implies delta P by mu L h square by 2. So I'm substituting y is equal to h. That's why it's h square by 2 plus c1h. Now c2 was already 0. So this is equal to this is equal to u naught. So in a way, my c1 becomes u naught minus delta P by mu L h square by 2 by h. Okay. So I have just I've taken this to the left hand side and then divided. That's why I will get this. Now I put back c1 in u of y. So I get delta P by mu of L y square by 2 plus c1 which is u naught minus delta P by mu L h square by 2 by h into y, and this is equal to u of y. I'm just moving the left hand side and the right hand side. U of y is this. And then finally, this is all just rearrangement. It's not too bad to do. Mu L h square by 2. You get y by h into minus y square by h square plus u naught y by h. So this is my u1, and I think this is what the problem was asking for. I believe, let me just check. 6u1 rather, okay? 6u1. Okay, that makes sense, Talal?
Yeah, thank you so much.
Yeah, for sure. Other questions?
How did you end up like, how are you able to say that that's 6U1? Are you just like, you realize, is it just pretty much that like the rest of the like U of Y is like identical? So you're just saying that-
Exactly. Yeah, exactly. Yeah, exactly. So whatever is the prefactor with this term, that's 6U1. So for instance, like because we have been given a velocity profile and that's supposed to be a hint for you, right? So that you don't have to carry around the terms and do much. So basically, this is a hint that whatever is the prefactor of y by h minus y square by h square combined, that's the 6U1 part.
Perfect, thank you.
Yeah, for sure. Other questions?
I know you kind of already said this,
Mhm.
but like in this instance, like this is a pressure drop problem.
Mhm.
If it's like a pressure drop plus the like shear stress or whatever,
Mhm.
like how does this problem change?
So there is a shear here. So note that there is the top plate is moving. So it is still also a pressure drop plus shear.
Oh,
Or
okay.
yeah. So basically, when the both the so if this one any one of those values are non-zero, or both of them are non-zero, basically it's a combined shear and pressure driven problem. So this is a general approach. Basically, this approach is exactly going to be the same, whatever problem happens. The main changes happens in this boundary conditions and the coordinate system we are using. So maybe y goes from minus h to plus h, right? Or goes from 0 to 2h. In this problem, we are going from 0 to capital H. But if you remember from your class, we went from minus h to plus h. So the coordinate system changes. So essentially, this boundary condition might be u of minus h is equal to 0 and u of plus h is equal to u naught. So that's a choice that we make depending on the system and so on. So the problems will see variation in that, but the methodology is pretty general and will work for any pressure driven flow, a shear driven flow, or a pressure plus shear driven flow.
Awesome. Thank you.
Sure. Other questions? Anyone? Feel free to unmute. We have a few students here, so I want to make sure if others have questions, I'm happy to answer. Yeah, I mean, seems like I'm happy to take questions from students who have already asked because nobody else is asking questions right now. And you can also put your questions on the chat. Okay, so if you don't want to unmute yourself, you can put on the chat. I'll make sure to answer it. But we have plenty of time. So yeah, Owen, go ahead.
So on 5A, it has to show that the velocity profile satisfies the continuity equation. And on the solution, the whole continuity equation includes dvz over dz. I'm just wondering why that wasn't like included in your solution. Like I understand because that's 0, but like I don't understand why. So
Yeah, for sure. So basically your question is, let me see, show to you A by R plus B R E theta hat, right? So I mean, you can also, so remember a full solution, a full cylindrical equation should have had something with an ER hat, something with an EZ hat. So VR is equal to 0 and VZ is equal to 0. So whatever is the coefficient of EZ hat, that's your VZ. What's the coefficient of VR hat? ER hat, that's VR. So in this case, there is only one non-zero velocity, that's the E theta hat. So actually, I don't even have to worry about the VR. I can just simply say, is 1 by R del V theta by del theta equal to 0? Because the rest of the terms are anyway 0, because those velocities are not present. And that's true because this is not a function of theta. So that holds. Make sense?
perfect. Thank you.
Yeah. Other questions?
Can you go over
I
the
sorry.
Yes. Yes, Sophia, go ahead, and Talal, I'll come back to you. Yeah. Sophia, go ahead.
Okay. Can you go over 5C? I understand how you did everything up until you get to like the final what is that symbol called? Is it Xi, I think?
Yes, I, yeah.
Xi, yes. Um, because I was able to get the psi of each of them, but when you combine them, I got a little bit confused.
For sure. Yeah, no, I understand that. So let's do that. So let me, so 5 of C. And so just to kind of back up a little bit so that we can see, so del psi by del y is equal to minus, and I can do this so that others are also following, just to repeat the step, minus b of y. And so if we integrate now, so psi is equal to, and in this case, the derivative is on the top for this one, so y squared, and we're integrating with y naturally. So y squared has a derivative on top, so it becomes minus a log of x squared plus y squared by 2. Y half, because the derivative should be 2y on top, so we create a 2y by dividing by half, and so it'll be basically log of x squared plus y squared by 2 minus b y squared by 2, again integration with y, plus c1 of x. And this is very important, Sophia. So this is c1 of x. So whenever we are integrating with something which is a function of y, you can have a constant with respect to x. And so that's why the c1 is a function of x. Then now with the other side, we have minus del psi by del x is equal to ax x squared plus y squared plus bx. And now if I integrate again, the negative can go this side. It will be a log of x squared plus y squared by 2. And there is another minus sign, because of the negative sign, minus bx squared by 2 plus c2 of y. Okay, so now is where I think you are confused, is how did I combine them? So note that I need a function, I need these to be equal, right? I need these to be equal because they're both essentially the same psi. So I need the psi to be equal between these two equations. So how do I make sure that my top equation is equal to the bottom equation? So that's the point. So what am I missing in the top equation that is present in the bottom equation? So I see that minus bx squared by, so this is common, right? And so minus bx squared by 2 is missing in the top equation. And luckily it is only a function of x. So I'm allowed to add it. In the and the same in the top equation, I have an extra minus by squared by 2. So I can basically I can say c1 is equal to minus bx squared by 2 and c2 is equal to minus by squared by 2. And so that when I write psi, I get minus a by 2 log of x squared plus y squared minus b into x squared plus y squared by 2. And so this becomes minus a by 2 log of r square minus b r squared by 2. And this is minus a log of r b r squared by 2. Does this make sense, Sophia?
Yes, that makes sense. Thank you.
Sure. Okay. Perfect. And you can still have some other, like you can say some value, like a number here. I have like another c there. That's not that important, like another constant. But like I said, those number value, like numeric functions of x and y have to be included, but you don't have to carry around this extra c that I have in the solution. Even if you ignore that, you will not. But function of x and y have to be consistent.
Okay, thank you.
Yeah. Other questions? I think it was Talal who had asked a question. And since I want to go with Talal, yeah, Talal, go ahead, please.
Yeah, I have a question for question 3 in the practice exam as well. For
Go ahead.
the question. You wrote in the answer key that Q1 over Q2 equal to R1 over R2 to the 4. Then how did you go from this step to 2 to the 4? Because R1 is equal to 2R2. So if you divide R1 by R2, you will get
2.
1
Yeah.
2.
So
2.
no, R1 is equal to 2 R2, so R1 by R2 is equal to 2, right?
Oh, okay. Yeah.
Yeah.
Thank you.
For sure. Yeah. And as a qualitative feature, remember for the same pressure drop, the smallest flow rate will be from the thinnest pipe. Okay. So numerical values aside, always remember to check that it's always harder to flow something through a narrow constriction. So Q1 by Q2, Q1 should be higher because it's a wider pipe, and Q3 should be the maximum because that's the widest pipe. So lowest flow rate should be from the smallest pipe, then the for the same pressure drop. So yeah. All right. Other questions? Anyone? Yes, Nicole.
Question two.
Yeah, go ahead,
Sorry.
Nicole.
For this question too, I was just wondering for the integration of the stream function, should we be able to like just do that integration pretty fast, or should we expected to like know those integrals pretty quickly, or would they be like a little bit easier than that?
Yeah, I would say this was a little bit of a harder problem in the practice exam. So what you will see tomorrow will not require this level of integration. But in general, I would say use your time wisely. So there might be some problems that will have more integration to make sure you do attempt the problems that you're comfortable with. But I do assure you that tomorrow's exam will not have the level of integration like this one, particularly. I think was a little bit on the harder side and required a bit of sort of memory. But it's okay. Tomorrow won't be like that. But in general, be a little bit conscious of time. So this exam, because of the mathematical nature of integration and differentiation, tends to be a bit on the longer side just by nature of it. So but it will be representative still of the difficulty level of this one, but this level of integration won't be required. Yeah. I think somebody Ari, Ari, go ahead, please. Yeah. Ari, do you have a question?
Yes, I have a question on one of the iClickers.
Sure, yeah, please go ahead.
It's question lecture 13, question 1. And it's asking about it says under what condition will the system behave like a 180-degree turn tube?
Yeah,
And
yeah,
I'm just having a hard time conceptualizing that.
for sure. Yeah, so this is iClicker lecture 13 question 1. Lecture 13 question 1. So so this is the tube here, and I'm just kind of going through the geometry so that I sketch it right. And this way. So this is U2, and this is sorry, the opposite way. This is U2. This is U1. Yeah, this is the theta, right? So your question is, how do we know what's the how do we think of a U-turn and so on? And so basically, the way I would put it is this: if this theta, if this pipe hugs the x-axis, right? If it's so, this is y, this is x. If this side of the theta, right, hugs the x-axis, that's essentially it's the angle you make with the x-axis, right? Right. So if I have a U-turn, like sort of this pipe, U1, so this essentially is hugging the x-axis. This is what I need by a U-turn, right? So you're going this way and then you're coming out this way. So this would be when theta is equal to 0. Now on the other side, if I have a pipe kind of like this, then note that the x-axis, because think about the direction of your U1. In this, U1 is going positive x, and in this case, U1 is going negative x. So the angle is basically theta is equal to pi in this case. Make sense, Ari?
Yes, that makes sense. Thank you.
For sure. All right, perfect. Other questions? Yeah, Owen, please feel free to ask question. Yeah.
I just have a general question. Is like the average velocity equation for like the Navier-Stokes stuff and like the shear force equation, like, is that equation consistent for every single question that can be tested on, at least in this course, or
Yeah,
is there more things generally that like we should know?
No, no, for sure. The Q is equal to V dot ND is actually true for like for any system you will study. So this is a general equation anywhere. And in the Cartesian problems, this becomes U dy of width. So this will be fine for you to kind of remember as well in your exam. The shear stress, I would say, is there is a more general form in fluid mechanics, but for the purposes of your course, you should just remember du by dy and then choose your plus minus sign correctly. That's it. Yeah. So that's all you have to remember for this exam and this course.
Good deal. Thank you.
Mhm. Yes, Jody, please go ahead.
Can you like explain how you solve for homework 5, problem 3?
Homework 5, problem 3. So, okay, just give me 1 second. Sometimes I have to go back and look at the homework. All right, sounds good. Homework 5, problem 3 for sure. So let me. Oh, is that the Bernoulli's problem?
Yes.
Okay, sounds good. Yeah, just I'm just making sure the values are correct. Right. So homework 5, problem 3. All right, yes. So homework 5, problem 3. Right, so we have a system here, and then we go from here to the point here, and we have been given the point A here and point B here, and the fluid is flowing down like this. And so the question essentially is asking us if the friction between A and B is this sort of 0.8 V square by 2, determine the flow rate of in feet cube per second. So the real main point here is the modified Bernoulli's equation. So why modified Bernoulli's equation in this problem? So why is because we have been given friction. Okay, so a siphon problem that we did before in part 1 of the class never had any friction because we were just completely ignoring viscosity. As you are seeing in the other parts of the class, viscosity is pretty complicated. It does make life difficult. So that's why people sometimes denote this sort of friction or make it like a loss just so that they don't have to deal with all this velocity profile and so on. So it's kind of like a simplification people do. Now, because of friction, I hope it makes sense that the energy at point A would be higher than energy at point B, because if I'm going from A to B, I'm losing some energy because of friction, right? So pressure, and total energy at B is lower than the energy at A. So in a way, and we will use the V square by 2 because that's the loss we have been given. So we'll use the units of the rho V square by 2. So there is no velocity at point A plus gamma z of gz of A. This is the units. When you divide by the density, you get this as the formula, and then you will have PB by rho plus GZB plus rho V square by 2, and this is the usual Bernoulli's. But now I will add this 0.8 A V square by sorry, not rho, just V square by 2 here. I will now add this 0.8 to compensate for friction, because again energy at A is higher than energy at B. So I'm adding this on the right hand side, or you can subtract from the left hand side to compensate for loss of energy. And it's 0.8 V square by 2. Why is this same V here? Because this is the velocity in the siphon, which is given in the problem. And so from here, and the PA and PB are the same. So essentially GZA minus DB is equal to 1.8 V square by 2. From here, we can calculate 0.9 square root. And so from here, then you can calculate flow rate. Make sense, Jody?
Yes, but I'm at some point when I was trying to relook at the lecture video,
Mm-hmm.
some point that the video voice like kind of cut off
Mm-hmm.
at modified Bernoulli's, and I was like, I want to know specifically what E loss plus W gain like specifically mean.
Yeah, for sure. So let me first say for tomorrow, don't worry about this, and this is not going to be the focus for tomorrow. But in general, basically, whenever you are losing something, so think of it like this. So if I have PA plus rho A VA square by 2 plus GZA, this is my usual Bernoulli, right? So plus rho B VB square by 2 plus GZB, then the energies are equal unless I'm losing some energy, which is minus E loss, or I'm adding some energy, which is my W gain. And that's how I can equate these 2 points together. Make sense? Like
Oh,
it's like just like a way to do an energy balance if you're inputting some energy and losing some energy as well.
okay, got it.
Yeah, perfect, for sure. Anything else, Jody?
Not really,
For sure.
but
Okay.
thank you.
For sure, yeah. Other questions, Owen? Go ahead.
I just have an in-class verification. You
Mhm.
said that for like for Navier-Stokes and stuff like that, we're just using Cartesian coordinates, right? We don't have to
Right.
worry about how to do it cylindrically.
Yeah, you don't have to worry about cylindrical, but the cylindrical coordinates is expected for the continuity and stream function, but not for Navier-Stokes. So
Okay.
like the one, I think homework 7, problem 3, which is the pipe flow, that's something you will not have to derive in the class. You can just use the results, but the Cartesian coordinate will be expected. Yeah,
Awesome. Thank you.
sure. So modified Bernoulli's, don't have to worry about it tomorrow. Yeah. Question on the chat was about modified Bernoulli's, don't worry about it. All right, other questions? Let's see if there is anything other than on chat. Sorry, Mehmet, but I was wondering if you could explain what we should expect regarding circuits. Yeah, so for circuits, you should essentially expect kind of like the one you saw in the practice exam. So, what if we have 2 pipes in series, and like very thin pipe here. So what will be the flow rate in such a system? If I've been like a formula, you won't be asked to do any like fancy calculations in this, but just to make sure you know it's omega 1, omega 2, omega 3. So omega is equal to omega 1 plus omega 2 plus omega 3. Or you can think of a problem like you have in the practice exam, like parallel. So that's it. You won't be expected to do any more than simple series and simple parallel. So simple series circuits and simple parallel circuits. So there is not going to be a circuit where we'll expect you to do something combined series and parallel. So I wouldn't worry about that. Other questions here? If not, Owen, you can ask question. You see your hand is raised.
Is that series one on is that the exam review that we did on Tuesday where we can find that example or?
So yeah, so on Tuesday, the lecture had a series example. Yes, correct.
And my other question is like, for number 3, it's parallel and it's asking about like, the relationship of the flow rates.
Mhm.
Can you ask like, what's given, like if you give us flow rates, what's the relationship of like radiuses and stuff like that? Or is this
Yeah.
strictly like a flow rates question?
No, that can be asked. Yeah. So you can be asked the reverse question. So in this question, so in the voltage and currents term, in this problem, we gave you the resistances and asked you the currents, but we can also give currents and ask for, I think, resistances. So, and from resistances, you can extract the radii. So yeah, so that can be asked.
Awesome. Thank you.
Yeah, Ari, go ahead. You have a question.
Can you just real quick go over how to identify the sign for shear stress?
For sure, yeah. So for shear stress, yeah. So sign for shear stress. Sign for shear stress. So as I said before, for this course, you can use mu u is equal to du by dy when u is only a function of y. There's a plus and minus. So how to choose sign? Choose sign. So in simple words, in a simple words, I can just say the top plate would be a negative minus du by dy, because it's the normal is pointing towards downwards, and the bottom plate normal is pointing upwards, so tau will be plus mu du by dy. So if it's a top plate, it's a negative, bottom plate, it's a positive. So because of the normal direction, and that's because we are only asking you to solve in the Cartesian coordinates for Navier-Stokes, I would say that that's what you can just focus on. Make sense, Ari?
That makes sense. Thank you.
Sure. Other questions? We still have 10 minutes or 9 minutes.
Just like the practice exam, Navier-Stokes continuity and coordinate change is going to be given.
Correct. Yeah. So the last page is repeated. Yeah.
Awesome. Thank you.
Yeah. So that doesn't have to go in your cheat sheet if you're bringing one. Yeah. That'll be given. Anyone else? We have a few students on the call. Feel free to unmute yourself and ask questions. And yeah, just to remind you, there is another review session from 5:30, I believe. That'll be led by Julia and Jonah. That I think is in A104. So it's a pretty good room. Feel free to also go there. And that'll be in person. And I'll make sure to post all the notes and the recordings as well, but like in a few hours. Yeah.
I suppose if no one else has any questions, can we just finish problem 6? I know we already did part A, but can we just do B
Yeah,
and C? Because
For sure. Yeah.
I want to.
Yeah, so the problem we did get so 6, and I think we just need the 6U1 and all now. It doesn't ask you to go back to the delta P by L, right? So there's a flow rate and then the shear stress, right? And let me just now go practice exam 6 B. That's the flow rate, right?
It's asking for average velocity.
Yeah, okay, average velocity. Okay, so finding the flow rate is the first step, is U dy times width. And we'll go from 0 to h, because remember the plates are going from y is equal to 0 to y is equal to h. Then we have w is equal to 0 to h. Velocity is 6u1 times 1 minus y square by h square plus u naught y by h. And all of this is dy. So now integration, so we can think of it like this. Integration of 1 is simply y. So 6u1 y. Integration of y square is y cubed by 3. Is y cubed by 3h square. Okay. 3h square. And then we go from 0 to h. And then we have u naught into y square by 2h. We're going from 0 to h. Okay. So this is my integration, and I'm putting the limits. And now I have width w. Then I can say 0 to h, if substitute just becomes h. Actually, sorry, apologies. I was thinking, why am I getting this wrong? The velocity profile was y by h. Apologies. Y square by h square. This was the velocity profile, so I think I just misremembered. And so the velocity profile will be now y square by 2h and minus y cube by 3h square. Instead, so it's y integration of y is y square by 2, integration of y square is y cube by 3. So we get 6u1 into h by 2 minus h by 3. I'm just substituting the limits. Then here I'm taking the limits again. So I'll get u naught into h by 2. Okay. As you can see, h by 2 minus h by 3 is h by 6. So I simply get u1 times h plus u naught into h by 2 times width. And u average is simply q by w times h. It's h because that's the width. If it was twice height, it will be 2h. And this comes out to be simply u1 plus u naught by 2. Okay, so this was the part B. I don't remember part C. Can you remind me if it's the top plate shear rate or the bottom plate shear rate?
It's the top plate.
Okay, so top plate has a negative sign. So it's mu du by dy at y equal to h is minus mu d by dy. Again, it's 6u1 into 1 minus y square by h square. I just have a habit of writing it like y by, just y by h minus y square by h square plus u naught y by h. Taking a derivative of this, so taking the and add y equal to h. Okay, so derivative of y by h is 1 by h, so it's 6u1 into 1 by h minus 2y by h square, and this is at y equal to h, and there's a negative minus mu outside, plus u naught, y has a derivative of 1, so it's u naught by h. Again, there is a minus sign on top, outside. So this becomes, if I substitute y is equal to h, it becomes 2h by h square, which is 2 by h with a minus sign. So it becomes, total becomes 1 minus 1 by h. So it's 6u1 by h with a negative sign, but it will become a positive sign because of the negative outside. So it's mu 6u1 by h minus u naught by h. This is shear force per unit area.
Thank you.
Sure. Yeah. Other questions? Any other questions? Anyone? I have something on the chat. I think I am here for another few minutes if anybody has questions. Any questions from you, Jody?
I don't think so.
Okay, sounds good. I'll stop recording now. I'll stop recording.